once more. So why do we discuss all these filters? Very asked at the end before the lunch break. So we discuss these filters because we want to. This is a basically didactic trick by Feynman to show how amplitudes of state changes in quantum mechanics are calculated. So you can see this filter as like a state of a particle, because the particle that has gone through this filter has spin up. So this filter so this filter has ensured that every particle that goes through it is spin up, because the magnetic field has pulled only the spin up particles up and has blocked those off. Yeah, so let's review this once more, how this filter works. So here. So the particles are split in 3 beams, they are put together in 1 beam, and then they're going through this. And basically by doing this, so this is a unifier, the last. And if you put into the middle one, in the middle apparatus, if you put there a filter in, then the particles of this beam will all be spin up, and this is how the filtering works. And so with the Stern-Gerlach apparatus, you can basically create a filter to filter for quantum states. Now all the particles in this that come out here have spin up. Here, all the particles that go through this filter can have any spin, but because they come only spin up particles from here, at the end there will still only be spin up particles. And here then again you have a filter that lets only spin up particles through, so that here you have also only spin up particles. So now we are asking the question, how likely is it, what is the amplitude of going through this, from this state to this state, right? And so the amplitude is, the amplitude will go from this state to this state, multiplied the amplitude by this state to this state. And now we can go plus, 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 plus 0, plus, minus, plus. And if you add these 3 products together, you get the probability. And now what is important, and why I showed this, is that if you abstract this by replacing the plus, plus with 0, 0 and minus, minus, you can write E. Yeah, and this E is then a variable which can take on any of these 3 values, and these are called the base states. And why the base states are important, we'll see in a minute, but that's why Feynman makes a sorted space parameter. And now we have seen that the complement of the amplitude is this. So when we square the amplitude to obtain a probability, that's the same as multiplying this amplitude with the complement amplitude. And so if you look here, what that means, so that means that the complement of S, the amplitude of S to T, times it plus this complement times this plus this is 1, and this is the same here. So, but these 2 equations are only consistent for all relative orientation of T and S, only if this is true. So if S, so the amplitude to go from T to S equals the amplitude of S to T complement, the amplitude of 0T to plus S is equals to plus S to 0T complement, and for minus as well. So that means that basically from this you can follow that the amplitude to go from chi to phi is equals the amplitude from phi to chi complement. And that's very important for later on. So this is a basic law of quantum mechanics. Now the filters have all been illustrated. The filters have now been used to illustrate the 3 basic laws of quantum mechanics. So the first basic law of quantum mechanics is that the likelihood to go from one state to the other equals the Kronecker delta. You've seen this here. So that the likelihood to go from plus S to plus s is 1, from 0s to plus s is 0. Yeah, because a particle that has 0 spin cannot go through the plus spin filter and so on. And so this is this is the first basic law of quantum mechanics, that the amplitudes to go from one state to the other state is only one if the states are the same. This is delta here. That's the first law. We've seen it now. We've derived it using the filters. We've also derived from the filters that the likelihood, the amplitude to go from state phi to state chi equals the sum of the products of the first amplitude with the base state and the same base state with the second state. And we have to make all these products and add them together over all the base states to obtain the amplitude. And this has been also demonstrated with filters. And finally, we've used the filters to demonstrate that the amplitude to go from one state to the other equals the amplitude from the other state to the first one complemented. And these are so the filter thought experiments by Feynman are used to show the three basic laws of quantum mechanics using the filter. And now, so this table that you see here is basically the state transition table. What is the amplitude to go from one state to the other state? And we see here, as I said many times now, that it's only one if I go from the same state to the same state. Now we can review once more this transition table at the middle. So, so now we have an S apparatus that filters only positive spin up particles. And another apparatus which we call S. We have another apparatus called R, which filters only spin zero particles. And in the middle we have what, this is a direct quote from Feynman, we have a complicated mess of junk which we call A, and then this R apparatus. Now, with what amplitude does a particle that enters the section A in the plus S state come out of A in the OR state, 0R state, so that we get through the last filter R, and that is the amplitude plus S A R 0 0R, and that's start through finish, and you can express this also phi A chi, and that's also an extended version of the Dirac notation, where between the two states that you have here, you have now put in an operator called A, and this is this in the middle. And to understand this, so if we now would decompose this A into two twisted filters, the T-type filters, which were tilted a little bit, and we call them plus or minus and plus or minus. So these are twisted filters which don't filter for anything, so pass through ones, but they are turned by a certain angle. Now the amplitude for each pass is, of course, from here to here, plus S times one of those. Yeah, this is the plus S, the amplitude from plus S to I, which can be plus T, 0 T or minus T. Then we have plus T, 0 T or minus T, which is the I again, to A. Then we have A to plus T, 0 T or minus T, which is J, and then we have plus 0 R, plus 0 R, 0 plus TR, sorry, plus T to R to 0 R, 0 R to 0 R, or minus T to 0 R. So this is the amplitude for each path. And so the total amplitude, if we sum over the I's and J's, we get all the possibilities. And the general result we obtain is this. So this amplitude to go through a middle operator, which is this A, from phi to chi, is this expression. And this basically is a decomposition of the amplitude from phi to chi as a sum. And later on, we will learn that this can also be an integral. And so if we look at it once more, so that means that that this expression, the amplitude to go from I to j via the operator A, can be written like this, right? So here it is plus A plus, 0A plus, or minus A plus for the first row with pluses as a goal and plus 0 and minus as a starting point, and so on to fill the entire matrix. And then this can even be expanded. So, so we can have a filter C here between S and R, which then we would write phi C chi, or phi C chi. So C would be the filter, but this can also be made up of two filters A and B connected via base states K. So we can also express filters as products of filters, and or later on operators. And the whole purpose of this filter story is that they can be used to really in a nice way show how relate quantum states to mathematical expression. So this is a quantum state because I filtered the particles through, and I have now only let through particles with positive spin. So this is a real quantum state, and I have three. And now I can write them in this way, and the whole story, this is an entire chapter, in fact, which I have now summarized. The purpose of the story is to show how the mathematical model relates to the reality of what is going on with the filtered quantum particles.
So can you just give some concrete examples of what you mean by quantum states?
So we can skip on a bit. Yeah, we don't have to skip on, we can go back and see. The quantum state, so we have here a mixed beam of, this would be spin 1, so that would be deuterium. So hydrogen with an additional neutron in it, going through the Stern-Gerlach filter apparatus. And then this, so they have, with regard to the quantum property spin, these here have spin up, spin 0, and spin down. So these are three quantum states. So, and you can imagine as spin up, spinning in one direction, spin down, spinning in the other direction. Yeah. And spin 0 not spinning. And so because we have learned that every atom is itself a small magnet, when it spins up, it gets pulled up. When it spins down, it gets pulled down. And when it doesn't spin, it's in the middle. And so these are three quantum states. And this Stern-Gerlach apparatus has now separated all the atoms that are in this beam in these three states. And now I can for example, take these atoms and use them. And I know that they are all in this state, because I filtered them or separated them with a Stern-Gerlach apparatus.
And does this happen in the ordinary world, or does it only happen in special kinds of equipment?
So in the ordinary world, all the spins of the atoms are mixed. But for example, if I now, I mean, where does magnetism come from? It comes from Bernstein. What's Bernstein? You know the
Bernstein.
Bernstein in English?
Yeah.
What is it?
Bernstein.
Know? It's also Bernstein. So if you rub Bernstein on a tissue, you get electromagnetic field, right? And so this was how so in classical Greek magneton, no, electron. Electron means Bernstein. So basically that's how electromagnetism was initially discovered in classical antiquity. And so you have these phenomena in reality. Yeah? You have electromagnetism in reality, and whenever it occurs, or magnets, you find magnets in natural. The Earth is a gigantic magnet, for example. And so if you find these phenomena in nature, they are all based on this. So this filter is a way to analyze the properties of the particles. Of course, in wild nature, there is no Stern-Gerlach apparatus. However, the Stern-Gerlach apparatus allows us to analyze a certain property of nature. And so these are the three quantum states, and the filters that we've described later, which is this one, which basically blocks out two of the beams of ions, of atoms. This basically helps us to then obtain pure states of quantum states. And the whole purpose of this chapter is to show how these filters relate to mathematical operations. And I basically can represent the probability of going from, for example, spin up to spin down for a particle or from one location to the other, from one amount of momentum to another amount of momentum, by the sum of the product of the the amplitude of this state going to one base state, and then from the base state to the other state.
And now, you haven't mentioned this yet, but I think it might be useful to mention, if it's true, that this spin-up, spin-down business is very relevant for the understanding of quarks.
Oh, I mean, we will not get to quarks, but quarks are because we are not covering in this course high energy.
No, but just so that people see that this is of general interest, the spin-up.
No, but the quarks are not. The spin of quarks is really different from the spin from the spin that we are. So this is important because magnetism is explained by the spin, right? Okay. So and magnetism is an ubiquitous phenomenon. I mean, everywhere there's electric field, there's also magnetic field. So it is magnetism is as ubiquitous as is electricity, and so therefore it is the spin is the reason why spin is interesting because it is what causes magnetism.
Okay.
Yeah, and that's the reason. I explained this when I explained that each atom is a small magnet, right? And so.
Jobst?
Yes.
Is there a reason you grabbed the spin 1 particles for your examples?
Yes, because the spin 1 can create 3 states out of it. And with spin 1/2 I can only create 2 states.
I know, but why did you want to?
And then I don't have the nice matrix. So I want a 3x3 matrix.
Oh.
And so the and because the 2x2 matrix is basically too simple to explain, later on the matrix will become bigger.
Of course,
you don't understand how the probability, how the amplitudes are calculated without at least 3 states. Yeah, so therefore you need, so it's not me, but Feynman chose this example because it's the simplest one, with which you can understand how later on the Hamiltonian matrix will come about. So that's
fair enough.
Okay, now let's look at the next point, energy, amplitudes, and time. So when we have 2 waves of similar wavelengths, so this wave is, as you see, a bit slower than this wave. But if you superimpose them, then you obtain a superposition wave, and that's a beat. So basically, beats that you hear in music are made by superposition of waves with similar frequencies. And so these are the frequencies, the wave frequencies O1 and O2, and which are also called angular frequencies, but these are the wave frequencies O1 and O2. We'll get a net resulting wave of average frequency 1/2 times their sum, which oscillates in strength with the frequency of O1 minus O2. And so the average time of the 2 waves, so this is the wave equation for the 2 waves, and you see here these are the amplitudes A1 and A2 of the waves, and this is the wave frequency, and now you can basically factor out the average of the 2 waves, and then you have a high frequency wave with a modulation of the lower frequency, right? So this is what you get. And if you think of an energy of a particle at rest, so then the amplitude to find a particle at a certain point in time is defined like this. So it is some factor a times the exponential function minus I multiplied with the basic energy divided by the Planck constant times time. And so this is equals, this equals E0 divided by the Planck constant equals the angular frequency or the frequency, and this is the angular frequency times the Planck constant is the basic energy, and so you see if we plug this in here, the 2 Planck constants cancel out, therefore we don't have a Planck constant here. And this base energy is the mass times the square of the velocity of light. And so if we have now 2 different energy states, then the only difference is that they have a different frequency. So only this will differ.
So To have a definite energy is to be at rest?
Yeah, I mean, yes, a moving particle. Of course, if a particle moves, its energy will change usually, right? Unless you supply it with additional energy. So what is important here in this equation is to see that that the only thing that determines the energy of a particle is the frequency. So the frequency of the wave, and we've seen this before. So this particle, if this would be a particle, that has slightly more energy than this one because it's oscillating fast. And now, in quantum energy, is the sum of kinetic and potential energy as in classical physics. So we've seen at the beginning this morning that you have to add kinetic energy so that the Hamiltonian is the sum which describes the energy of the particle is the sum of the potential energy and the kinetic energy. And so the amplitude of a particle in a constant field is proportional to this number here, of this equation. So you see here, you have the potential energy, which is the energy that comes about from the motion of the particle plus its potential energy minus its momentum. And this general principle is that the coefficient of t, this one, which is the frequency, is always given by the total energy of the system internal. So internal energy plus kinetic energy plus potential energy. And so this is very important. And so this is the internal energy. This is a kinetic energy, and this is a potential energy. And so here, when you have a constant electric potential, then the particle will just moves along like this. And it's just important to know that this term that we have here, right, is composed of these components. And the particle in a potential gradient moves under the conservation of energy. So we have already seen this. If we have here this this potential phi2 is more than phi1, the particle will move like this. And you see that here it's accelerating and that its velocity, its frequency is increasing. So its energy is also increasing. And so in the left-hand box, you see that the amplitude of the particle is the internal energy plus that's the potential energy P1 with momentum P1 plus kinetic energy P1 plus potential energy, and here it's kinetic energy P2, it's momentum P2 plus potential energy P2 minus always the momentum times the distance. And so also like so this is a quantum mechanical view of energy, and like in classical physics, it's also conserved. Yeah, so so if P2 is greater than P1, which is the case, then the wavelengths in the second box must get shorter. Yeah, so you see here that the momentum of the particle increases, so if this gets higher, I have to have shorter wavelengths so that I have conservation of energy. And this is basically the conservation of energy shown for the quantum particle.
And so on the pictures there, I don't see any quantum leaps.
So the quantum leap, you can't see it. So so remember that when we go back to the black body radiation, the curve for the black body radiation is continuous, right? The quantum leaps are only the contribution of each electron changing its energy level in a discrete fashion. But remember that this is expressed by the Planck constant here. But because all the variables are continuous, you still obtain a continuous result that is just, so to speak, scaled up or down by the Planck constant, right? So these are still continuous functions, and they are also differentiable and everything. They have all the good, nice properties of functions you want in mathematics. But their overall magnitude depends on this, and so that's where the quantum aspect of the equation comes in. And now comes something very, very interesting. So when the potential energy gradient between two regions is very high, and when V2 minus V1 is greater than pi 1 squared divided by 2m, then we have the following. So P2, so if you look at this equation again, we can cancel out the W in the internal energy, because internal energy stays the same. And for example, the internal energy of the proton is the movement of the quarks inside the proton, right? And so we can cancel out the internal energy. And then now we have, and we algebraically get this by actually just applying simple algebra, right? We have to multiply this by 2m and subtract V2. Then we get this equation, and now if this is greater than this, then this whole expression becomes negative. And classically, we would say that the particle. These are two regions of potential, right? And so if these are here, of course, the potential phi2 is higher than the potential phi1. There's higher potential here and the lower potential here. And because of the higher potential, we get the acceleration. I think I didn't explain this well last time. So now we look at the two boxes again. If this potential difference is very, very big, then classically we would say that the particle can never get into region 2. It doesn't have enough energy to climb the potential hill, because the difference is this is also potential hill, right? And if we take this potential hill, for example, and now I do this, right? A small child, good, I was lucky. A small child couldn't do that, right? Or a weak person with multiple sclerosis couldn't do this because the potential hill is too high. It can't overcome. This is quite a potential hill. I mean, I have a body weight of 72 kilograms, and I have to lift it up, you know, and so classically the particle would be like this weak person can't do this step, right? And in quantum mechanics, now comes something very, very interesting. It's like this. The space variation amplitude is looks like this. So here we have P2 in the exponent, and then here we have minus P prime x, and so what that means is this is a real number, because I have here minus e, so that's always a real number, and it decreases rapidly with increasing x, because x here is in the nominator. So what that means is that I have a kind of the potential goes like this, right? An e function with a negative exponent. It goes like this, and here's x, and as x gets bigger, it very rapidly declines, but it doesn't go to 0. It doesn't go to 0, and that's why a particle in quantum mechanics can overcome a quantum variable. So the weak person standing here in front has to apply a certain amount of potential energy, of kinetic energy, to overcome the potential barrier between the ground and the table. And in quantum mechanics, because of this equation, because this is basically the variation, space variation is expressed like this, right? It's an exponential function, and it looks like this, but it never becomes 0. It just gets very close to 0 with big x, and that happens very fast, because it's a negative exponential function, but it never gets to 0. And so therefore, you can, in quantum mechanics, a particle can overcome a barrier. So let's take a look at this. So in the first region, we have a low potential, and here we have now high potential. like the two boxes we had here, right? So here we had the low potential, here very high potential. Now, so this is a bit like, the left box is a bit like the ground and the right box is like the top in classical mechanics. And now, we have the particle is a wave, as we know. It is in the first region, and you want to get in the second region. But the point is that if you put in the x here into this equation, you can see the following. So here's the wave. That's again the real part of this e function that we've seen, the exponential function. It looks like this, and now we see that in this region where the potential is suddenly high, we have this effect that we've seen that the amplitude of the particle is dropping very quickly, right? But it's not going to zero. So the particle still has this chance of overcoming the potential, and which it would not have in classical mechanics. So Feynman says the exponentially decaying amplitude, right? Which we've seen here. This declining amplitude can reach across the region and give a small probability that the particle will be found on the other side where the kinetic energy is again positive. This is called the quantum mechanical penetration of the barrier. Yeah, and you can see it here. So here we have a region of opposed potential. We have the barrier, and here we have a region again of positive potential. So what happens is the particle has a certain which is V2 is now above zero, but as you see, yeah, it's above zero as well in both regions. Now the particle comes here. Here is a potential barrier where the amplitude of the particle drops, but it still has a chance to get into this region, and then here it will have a normal amplitude again. And this is called the penetration, the quantum mechanical presentation of a potential barrier. And what is interesting is, for example, and I think we will look at this example later, the radioactive decay of uranium can only be understood with this. Yeah, we have it here. This is an uranium nucleus, and when it has radioactive decay, it will emit a helium atom. Yes, a helium atom. And now this is called an alpha particle. And so, but the mean life of an alpha particle in the uranium nucleus is 4.5 billion years. So when you have a piece of uranium, on average, the alpha particle will stay there for 4.5 billion years. But in the nucleus, and I was talking about the energy of a proton, but the nucleus has energy as well. So in the nucleus, the nucleus oscillates inside 10 to the 22 times per second. So that's really very fast, right? That's the oscillation velocity of an uranium nucleus. Now, why is it like this? Because the exponential gives the tremendously small factor of e to the minus 45, which gives a very small probability of leakage. And so when the alpha particle is in the nucleus, there's almost no amplitude at all for finding it outside. However, when you take many nuclei and wait long enough, you may be lucky and find one that has come out. So this is you can see it here. So this is basically the potential. This is the how far is the particle outside of the nucleus, and you see here that here is a huge potential barrier that needs to be climbed, depending on the radius, and here you see then in a qualitative way. So this is basically the barrier that needs to be overcome. And then when it's outside, it has again a normal amplitude. And this happens only, it takes on average 4.5 billion years for one helium to get out. Because the barrier is so high. And this is very interesting, and without quantum mechanics, we could not understand radioactive decay. Because in classical mechanics, the helium, so this alpha particle would have to stay there in forever because it could never overcome this potential here. But in quantum mechanics, because we are now thinking in amplitudes of waves, I mean, this is really, in reality, this should be much closer here, very, very little, but there is still a positive amplitude that it can get out. And I think this is a very impressive illustration of the problem of amplitudes and location. And why quantum mechanics can explain, or this way of this model of the behavior of the particles is the only model we have that can explain this, and the classical model couldn't explain this, I think. Are there any questions regarding this part that we looked at?
Can you explain how they discovered this 4.5 billion year time lag? You can't wait around and watch.
No, you can count the number of particles, and then you can, so you have a huge block of uranium,
yeah.
You can measure alpha radiation, and then you can determine the probability,
okay.
Because you know how many nuclei there are in this block of uranium.
So how many particles are there in a 1 meter cubed block?
A lot.
I mean, the molarity, or you have to look at the molarity, and then you can calculate how many there are in a kilogram.
Yes.
And
but of the order of
10
to the 9?
10, no. Avogadro constant is 10 to 26
okay.
per mole. So,
okay.
And I think it's 120 molar, so you have 10 to 38 molecules in a kilogram.
Yeah.
Right? And so a cubic meter of uranium, I mean, that would be more than a ton. That would be, I don't know. So then you have really a lot of molecules. And so if you have a bigger amount of uranium, you can measure. So now we come other questions regarding this. So the take-home message is that first of all we have conservation of energy. Also although we express now energy like this, and we have an amplitude. We have to think in amplitudes with regard to the properties of the particle. We have conservation of energy like in classical mechanics, and we have this very interesting. So the amplitudes express probabilities of a certain location, and we have that even if we have a potential difference, this can be overcome because we now have the amplitude is expressed with an exponential function, and the exponential function never goes to 0. And I think that's very fascinating. And it shows you, I think that has a very high the theory describes what's going on. You can predict what's going on. I mean, you can't say out of this block of uranium which uranium atom will emit a helium, but you can calculate exactly how many will be emitted per day, for example. But you can't know of which it will come out. But you can say how many, and you have also an explanation. Now that's not a fully causal explanation, because you can't say that an equation explains causally what's going on, but it's a very good explanation, fully causal explanation, but it's a very good explanation to understand what's happening. Now the question is how can quantum states change with time? So we remember we had seen with the filters that the likelihood to go from the plus S state, which is created by the filter that only lets through positive spin, to the 0R state, which is the filter which lets only through the 0 spin particles. We can calculate this for each pass by putting in here the states of the base states in and multiplying this through, and then for all i's and j's we summarize it, and the general result now looks like this. And this is all only true for problem in which we have a finite set of states, right? So the i's and j's are states that you can number with natural numbers. So so for example, we look at 3 states: spin up, spin 0, spin down. For this kind of problems, we have the sum, and the state over which we build these results is called a Hilbert space, and we'll get back to the Hilbert space a little later. And now, if I have the state phi, and I let it sit, oh, there's a mistake again. Remove So if I let it sit, and then this function u of t2t, u1 yields state chi with the following amplitude. So basically, if I just wait for a certain time, then I have here first state phi, this is state chi, and now this operator u is time dependent, and it will tell me, it will allow me to compute this. And so which I do by summing again over the amplitude from phi to j, from j to this operator, from the operator to I, and from I to chi. So again the path that we've been talking about the whole time. And so so basically u, this function is a matrix of this shape. And now now if we have a state, what does the state look like in an infinitesimal time delta t later? So a very short time. So now we call the state at that time. So the states we had before, they were not dependent on time. Now we have a state depending on time. Now we ask the question, what is the condition after the small interval of time delta t later? Now this is the answer. So I have this cat, which is psi, a state psi of t plus delta t. So this tells me the function depends on t plus a little bit more. And so this gives me, as I know, this gives me this function u, which is used which is an operator that takes in c at time t and transforms it into c at time t plus delta t, and it takes as the two arguments. It takes the two arguments. And that works like this. I take the cat p of t and multiply it by this function that models passage of time. And now, so this is basically a cat with an operator in front of it, and this operator in front of the cat will basically change this to the time plus t, plus delta t. And now I can multiply this with a bra, which is the other state, and I want to find the probability in which this state is by multiplying it with this bra. And so this gives me, so if I put this bra to this cat, I have this expression, and now I plug in this, so I get chi, and then bar, I mean this sign, I don't know, and then the function, and then psi. So this is now the likelihood, the amplitude of going from psi to chi via the time operator. And now, or you can multiply this with any state. So this is basically a base state, so any state of the system. And then you get this equation, which where instead of the chi you have the I. Mm-hmm. And this can also, now you can also express the psi of t by the base states j. So now we say we have the amplitude of psi of t to go into state j. Then from state j we do the time transition, and then we get to state I.
Could you remind me what base states are?
So base states are, so we have not understood this very well, but basically in the simple example with the spins, the three base states are spin up, spin 0, and spin
okay.
down. And I think the most important slide to understand is how this works is this one. Yes, here this one. So here you can see T is an open filter which allows all states to go through. So when I move from plus S to plus S, so from here to here, I have to do plus, 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 which is this, plus 0 plus, which is this, and plus minus plus, which is this. So each time I have to construct a bracket with one of the three base states. And then I repeat this base state, so I come from here to one base state, and I use the same base state to go to this. And so these are the three base states in this simple setting. And so here I see that now I can express every transition from one state to the other as a sum of the products of going of the amplitudes, the product of the amplitudes from one going to one base state to the other. This is very important because it's very hard to understand what the sum is supposed to express if one hasn't looked at these filters. So this is why Feynman's book became, because why everyone is imitating this, because it's really the easiest way to understand base states in quantum mechanics. Okay, so now, so we have now this expression that tells us how the time operator is so to speak acting in this amplitude, sum of amplitudes. And now we look at this again, and we have learned that the likelihood of C after time delta t to get into state I is the sum over all the base states of t times this operator. And this is nothing but, so now we can let Ci of t be equal to this bracket. So Ct, amplitude to go from Ct to I. So now this here is a function that for each I that you want to know about, each target state, depending on time, we can calculate this. So this stands for the amplitude to be in the base state E at I at the time t. Then we can think of this amplitude varying with time. So each Ci is a function of time. So for one Ci, I can say after 1 second, after 2 seconds, after 3 seconds. So this is each now is a function of time. And if I calculate this, I just get a complex number, right? So it's a number with one component on the x-axis and plus another component multiplied times I on the imaginary axis. So I will get a complex number at each time point. And now we can, of course, write the above equation. Now I know that we have defined this is our time operator that moves a state over a certain amount of time into another state. Now if we plug this into the above equation, now we put here instead of t, we put t plus delta t, which is a small amount of time. And now we can basically multiply, we take this, and now this is interesting because here we have state I, and now we have state j, and by multiplying this, each state j with the corresponding u of the matrix, then we can basically for each t we can basically get a value. We can multiply this and add them all together, and then we get the time dependent expression for C. And now,
so hang on. The time-dependent expression means the probability that change will occur in that time.
The amplitude, not yet the probability.
Okay, the amplitude.
If I square this, then I get the probability.
Okay.
So it's the amplitude that state. So this is the amplitude that I will get from state psi to state I, varying with t. So before we had only this. We had only Ci equals I of C. And now we have just time. Now C has become a function of time. And to make it a function of time, and to model the passing of time, we use this operator. And this operator is like the A we had when we introduced operators. That was here. So this is an operator matrix, yeah, which says if I have an operator between two states, and I have now the 3 spin states again of plus 0 and minus, if I want to go from spin minus to spin plus, then I need to do this. I need to take this and wire this to this.
Okay, so is the story as follows? Matter is a gigantic mess, but if we want to understand it at the quantum level, our only hope is to use very precise kinds of filters, and those filters then allow us to calculate certain kinds of meaningful relations about this gigantic mess. For instance, having to do with amplitude changes after small time intervals in very, very restricted.
So this is a story so far because we have only looked at, right now we have only looked at at the three-state system spin up,
Yeah.
down, and 0.
Okay, so I was right.
And yeah, in this system you are right, but there are more complicated systems. But however, the basic principle is that we always need to build machines to measure one aspect, or to describe one aspect of the system, or a very few ones, and then we can use the equations to deal with them. But to already anticipate a bit, with the Schrödinger equation, which I think we will get to today, I think we are doing quite okay time-wise. With the Schrödinger equation, we can only calculate the states of the hydrogen atom and the helium atom. And other atoms which contain more particles, we can't calculate anymore. So for example, we will see the ammonia molecule, which is just CH3. It's just one carbon atom with 3 hydrogen atoms. We can't calculate anymore its behavior using the Schrödinger equation. Yes, you were first and then Tom.
I think we need to make a distinction between can't because it's really hard and can't because it's not possible.
I mean, not possible.
It's certainly possible.
No, the ammonia. There is no way to calculate the state of the ammonia molecule. It's impossible, and it's every physicist will tell you this. We can't calculate the state of the ammonia molecule. We can measure them, but we can't calculate.
Quantum mechanics has been used to explain chemical reactions.
Yeah. Yes, but we can't. But explaining chemical reactions is just explaining the behavior of one electron and another electron at the outside and of course there are many. So I'm not saying we can't do anything with quantum mechanics. I'm just saying that depending on what system we look at, we always need high abstractions. And yes, of course, we can look at very complicated molecules. But if it suffices to understand the reaction that's happening by looking at 2 or 3 components of them, then we can use the Schrödinger equation. It will work out wonderfully, and you will see great example very soon. So wait a bit, we are still only 1/3 through the course, right? But there are other systems which are quite simple, like the ammonia molecule, and we can't model the states of the ammonia molecule. It's impossible. It's really it's hard, but it is mathematically impossible. And that is very interesting, and I think you should wait a bit more, then you see why. Yeah? And basically, because the problem is that the space the state of the space state becomes infinite, and even with infinite space states we can still do a lot, and you will see also this in the course of the course. But what we can do is quite limited, and it's only possible to do this for very, very simple molecules. Only for the helium and for the hydrogen molecule can we really calculate through the full state space. But on the other hand, we will see very clearly that for a very complicated molecule, we can calculate exactly why it has a certain color. So why is this trouser brown? Because when the trouser was made, a dye was added to the trouser, to the cloth of the trouser. And you will see, maybe today even, that we can model this quantum mechanically in perfect.
I understand that. The part I don't understand, and I hope you will illuminate, is the impossibility of using these equations to explain something like
because there are rules in mathematics, in theory in functional analysis and functional theory. There are rules, and also in algebra there are rules that show which types of equations can be solved and which can't. And there are 2 ways of impossibility to solve a differential equation. One possibility of not being able to solve is a simple one, is not being to solve it analytically. And that means that you can still solve it computationally, numerically. And the other one is when you can show that you cannot that there is no solution space for the equation. And for many of these problems, you can mathematically show that with the mathematics we have, there is no solution space. Now, you can always argue, that's also the main argument against our book, that maybe one day we have a totally different mathematics. But with the mathematics that we have today, we can't solve it. And I believe that it's highly unlikely that we get a fundamentally different mathematics. But I don't know. I mean, I can't predict the future, but my impression is that our mind restricts what we can do mathematically. And for the problem for the ammonia molecule, we have mathematical theory showing us that we can't find a solution. So it's not, it's hard, and we can use a computer to get a numerical solution, but we simply can't. And when we try, and then make measurements, the results of the measurements will show that the computations were right, always. So that I mean, it's impossible. Now, Tom, what was your question?
Yeah, I wanted to address Barry's question. So I think you can think of those operators as granular partitions.
Yes.
The operators
Very good.
are matrices, and the cells are the eigenvector, the eigenvalues of those matrices. So the cells are the eigenvalues.
So we will, that's good, and we will hear more about this. But that shows you the equation you need to calculate now the passage of time. So you are multiplying, so as you said, so this is a matrix, like the matrix we've seen here, a matrix, sorry, like this one. Here, this is a, or it's not such a, let's take a simpler matrix, this one. This is a matrix, this U is a big matrix, and and the i's and j's are the rows and columns of the matrix. And now when you plug in, when you want to calculate this for the ith state, then you take the j's, all the base states j, which are the columns of this matrix, and the I is a row, and now you pick, for each j, you pick a cell out of the matrix, and multiply, and this gives you a row, this gives you the column, that's a cell, and in this cell, it describes what to make with these values when you plug them into the function, and then you multiply this with the amplitude. Okay, now let's see what this matrix, time transition matrix U looks like. So so far we don't know much about this matrix, except for one thing. We know that if delta t goes to 0, nothing can happen. We should just get the original state. So so that means that if nothing happens, that means that's II, right? So this is diagonal is 1, and that ij is not is 0. If I is unequal j. In other words, uij converges to the Kronecker delta for that delta t close to 0. So that means that when the time gets almost 0, then we have just a diagonal of 1 and the rest is 0. We can also suppose that for small delta t, each of the coefficients should differ from delta ij by amounts proportional to delta t. So that means basically that this matrix, to fill this matrix, we take uij, so this is some combination of rows and columns. We have this delta, and then for those, and then we add another operator multiplied by the time difference. And so if we say we have a factor and that we have always in the exponential, that is the unreal I divided by h. Now we factor this out of this. We have to put a minus sign here because we have the I, and then we get hij of t times delta t. And so these are the derivatives with respect to t2 of the coefficients evaluated at time t2, t1 equals t. So this is basically this is a matrix which contains the derivatives to t2 of the coefficients here, and this basically gives us the matrix. If we would have this matrix, we could also calculate the matrix U. And so now we have had already this equation that basically we have the amplitudes dependent of time plus the time difference equals this functional times Cj. We have also now seen that we can represent this matrix Uij as the Kronecker matrix minus these strange time derivatives of a yet unknown matrix. And if we plug this in, instead of the Uj, we get Cj of t, which is here, and then we get this expression which will be replaced by this. And if we sum over this term, we get just Cj of t, because we get, and we can then put on the other side of the equation and divide by delta t. And now we have, so this here is Cjt. We can put on the other side of the equation, and then we have on this side of the equation, we have this is left, and this we can get rid of the delta t by dividing it here, and this gives us that IH times Ci. You see immediately that this is a classical formula of the simple derivative, right? This is x plus h, f of x plus h minus f of x divided by the difference by h. So this is a really simple basic formulation of the derivative that you learn in analysis 1 and basic calculus. So this is just the same as this. So this is really the derivative, and so then we get this equation.
So can I ask my question again?
Sorry. Yeah.
So go back to the previous slide. So this calculation here again is done on the basis of the assumption that you have filters which are marked by I and j.
So this is based on the assumption that you have a finite set of states.
Yes.
So you may achieve them by filters.
Yes.
Or they may come about by different methods. So you now use the term filters in the two general ways. So the filter is just an example. You can also obtain these states, as we will soon see, and that will also help Alan to answer your question. That will also, we can also define this matrix in a totally different way. How we get to the states, but it just means that we have a finite number of states, and that we have now modeled the passage of time. This is quite a cool trick. So we say if the time is zero, if no time is passing, then only the same state, the function must give the same thing for the same time point. So therefore, it's a matrix of so time point 1 and time point 1 give 1, 2 and 2 give 1, and the others are all 0. And now that's this Kronecker matrix that we get here. Now, but if we have a small amount of time, we need to add everywhere to every cell of the matrix some other thing. And this other thing we can call Hij, and that's the Hamiltonian of quantum mechanics. So this is a way to explain how we mathematically get to the Hamiltonian of quantum mechanics. So we have two big assumptions. One big assumption, and for the moment, is that we have a finite set of states only. The other very big assumption is that typically this is so related, so you can see at a glance how this is related to what Newton and Leibniz did. Because basically you need the infinitesimal assumptions. This is typically infinitesimal calculus. And only with the tricks of infinitesimal calculus you can say, oh, if the time now is changing only very little bit, well then that means that I can add in this very little bit just to each cell. So this is 1, 1, to cell 1, 1, I now add, this is a 1 because I and j are the same. So I add a little bit of something multiplied by a little bit of time. And the 1, 2, which is 0, I also add a little bit of something and so on. And so this is another matrix now, which is, so to speak, added to the time matrix. And now I can, with another trick, by saying, oh, this matrix, all the elements of this matrix will contain the Planck factor, because I'm here in the quantum world, I just already factor it out. So it's really, it's thinking backwards from the goal. You can see how the mathematician wanted to do it. So I'm factoring this out. Now I can have the minus sign here, and now I'm already almost there, because now, as we've seen, we can use this to obtain in the end this. And this basically shows you, it's a very interesting case. It's not so hard to understand, because it's mostly, there's no integral here, there is no, the mathematics are not so hard, but you can already see how basically with the two assumptions of the finite space and the assumption of infinitesimal calculus, you then get to this equation.
So can you answer your own question here now without mentioning the equations?
Which question?
There. How do quantum states change with time?
I think in quantum mechanics you can answer nothing without mentioning the equation. I mean, you always need them. Once you have, so yes, I could try. So I mean, the way to say it is that an amplitude changes with time, which is this.
Yeah.
An amplitude multiplied by by an unreal number and the Planck constant changes with time is the same as I take the original time point with which I started of a certain of all the states that the amplitude can take on in this quantum model with a limit, and multiply this by the cell in my Hamiltonian that gives me the energy at that time point.
Okay, and that gives you the energy distributed across a number of equiprobable.
No, that gives me this here gives me the change of amplitude with time. So it's now not so time.
But where does probability come in here? That the amplitude.
Because this probability comes in here because this here, right? I mean, now I've calculated all this. Now I get this. Now this is a complex number. Remember, I have an I here.
Yeah.
So this is now the amplitude. Now if the probability comes, if I square this. If I square this, I get rid of the the unreal number.
Yeah.
And then I have a finite number, which if this, because of the design of this matrix, will give me a value between 0 and 1.
Okay.
And this will be my probability for the change of for the change that is happening over time that I'm observing. So this is how to explain words, but you see, you can try to answer the question, but that's all the answer you can give. Yeah, this is what physics tells us, and I just found this development of this equation of the Hamiltonian relatively understandable. It's mathematically not so hard. That's why I showed it. And so Feynman says we have arrived at an abstract formulation of the quantum mechanical law of the dynamics of the world. That's what Feynman calls it. and so this is again the photo of Hamilton. Hamilton is not so known among non-physicists and non-mathematicians. He was a British mathematician working in the 1820s and 1830s. I think he was an incredible genius, really. It's one of the people I admire most. This is a daguerreotype, by the way. So one of the earliest types of photographs that could be made. So now we have here this CIT is the amplitude CI to find bracket CI to find so bracket IP to find the state C in one of the base states I at the time t. So the equation tells us how each of the coefficients vary with time. Yeah, so I have now, no matter which state, I can choose any state and I can show how it varies with time. But that means it tells us how the state psi varies with time, since we're describing psi in terms of the amplitudes, psi I. So the variation of psi in time is described in terms of the matrix Hij, which has to include, of course, the things we are doing to the system to cause it to change. If we know the Hij, which contains the physics of situation and can generally depend on time, we have a complete description of the behavior of the time of the system. Hamilton was the first to derive a general framework for mathematical physics in the 1830s, long before quantum mechanics was invented. Yeah? And this general framework, we've seen the Hamiltonian for energy of classical mechanics at the beginning, and the Hamiltonian is, and Feynman then goes about, he's a bit upset that Hamilton, that is called the Hamiltonian, that Hamilton worked 100 years before quantum mechanics, but I think it's a good choice of the name because it's such an important discovery that he made. But this is kind of the first very big result of quantum mechanics that we have. And now the problem is, though, if you look at this matrix must contain all the information that you need to calculate the amplitude, or almost all. I mean, you also need the functional C, but we'll get to this later. But basically, it must contain a lot of information. And how do we get this information? This we will now see. And then, Alan, you will also see that the core problem is how to define the Hamiltonian, and that the impossibility of, for example, calculating the states of the ammonia molecule has to do with the inability to formulate a Hamiltonian that does the job. That's the problem. That we cannot always get such a Hamiltonian. So the Hamiltonian is equal to the transposed complement because the total probability of finding a particle does not change. So basically, when I have a matrix like this and spin it around, transpose it, I just turn it around by 90 degrees and replace every number, every complex number in it by its complement, then I have the same as before. And so the total probability of finding a particle is the sum over all the states squared. Yeah. And that does not vary with time, it's true for every starting state. And now now let's start with the most simple Hamiltonian that we know. It's a 1 times 1 Hamiltonian, it's just one number. It's one row and one column. So now we have again our minimal Hamiltonian, and we have now this equation here. So Barry, when do we want to do the first?
Yeah, I worked it all out.
So this would be, I just.
So the next break should be in 5 minutes.
Okay. So let's do this slide. So now we have this equation, and now I have a situation in which the physical circumstances are not changing with time. So the external physical conditions. So in this, then h is independent of time. Now, if we have only one j and one I, put this in, then we have here I times Planck constants times the derivative of C1, because I is 1. And now we don't have time dependence anymore, because nothing can happen in the matrix, right? It's just one number, so t goes away. And then we have equals, now let's sum here over the j, so we have the sum over 1, so we have 1, 1 of t, but we don't need of t anymore because it's just 1, so we have h11 or h11 times c1. And so this is now a differential equation. Yeah, and this is actually quite, if you disregard for a minute this term here, it is a very, very simple differential equation, because it just says, I want to find, so we didn't discuss differential equations here. But differential equations are just equations in which I have a function on one side of the equation, and on the other side I have its derivative. And why do I want such functions? Because such functions can show me how, so a function describes something, some effect in nature. And the derivative describes the change of the effect over time or over space. And so basically such an equation gives me, how does the situation change over time? And so this is a very simple differential equation, and the solution, when h11 is constant, because we say there's just one particle sitting there, then the solution is a constant multiplied times the e exponential function with this term in, I'm divided by h times h11 times t. And so this, and if you now take this, put this in here, and calculate through this derivative, both sides of the equation will be the same. And so therefore, a solution for a differential equation is always another function. And if you plug it back in, then both sides of the equation will be the same. That's a differential equation and its solution. And here you see a complex differential equation, because here we have a complex number, a complex number in there, and so this you get this solution. And this is the time dependence of a state with a definitive energy level E equals h11. Hij gives the energy and can be called the energy matrix. It is a generalization of the energy for more complex situations. Yeah, so this is basically, this is the most primitive situation you can imagine. One state, nothing is happening, and then you get this differential equation, and now you can, and what is happening? So something is happening. What happens when I put in t? I get such a wave. And that's because the particle in my quantum mechanics is modeled as a wave. So the exponential function with a complex number in gives me, when I plug in different values of t, then I get a periodic pattern that repeats with 2p. Yeah, so like this, and then after 2p, once I go around the circle, the pattern repeats. And this is my wave. This is my wave that I have here. That is the most simple solution. And now you can think of questions, and we have a how many minute break?
We have a 15-minute break.